Hey everybody, myself Yash Sharma. I'm a student of Bennett University and I am pursuing my BTech in computer science with specialization in artificial intelligence and machine learning. So today's topic is from high performance computing and the topic is Numa. What is Numa now? Numa is a non-uniform memory access. So we're gonna learn about Numa in this video, and from I can say that after this video ends, you will get a lot of information about Numa and some related stuff to Numa. Now, what is shared memory process? For Numa, since we want to know about Numa, so first we have to know what shared memory processors are. So it is a single copy of OS operating system, although some parts might be parallel. It is relatively easy to program and port sequential codes. It is difficult to scale to large number of processors. So as in our figure, we can see here are n processors having n number of cache which are connected by the interconnection network, and they're having a number of memories as m. So this here you saw a UMA machine block diagram. So you might ask, Yash, what is a UMA? So let me tell you, UMA is Uniform Memory Access. You will learn about this in upcoming time in this video. So how do we scale shared memory architectures? So in this figure we can see that there are multiple memories and the input output devices which are interconnected and the processors are coming. So what is the interconnection schemes for the shared memory? So the scalability is dependent on interconnect. So there are multiple uh, processors here and input output devices. There are multiple memories here. In this first, it is crossbar switch. As we can see, this is connected as like in switch substance. But where in multi-stage interconnection network, we can see that it is a bit complex. Okay, many are connected, interconnected to each other, many are connected, and here processors are connected to even the input output. As we can see, input output is going as like multi-stages, so this is called multi-stages interconnection network. So what is bus interconnect networks? Like in this bus there are two seats. As we see in the bus, there are the bus is like this architecture. There are two seats here, three seats here, two seats, three seats. There's like it is like this only. There are memory, there are processors, this is input output devices, memory, this is like this. So this is our bus interconnected network. Now, what is UMA? What are the types of shared memory architecture? So, UMA is Uniform Memory Access. So, it is access to all the memory occurred at the same speed for all processors. But now, for today, we will focus on Numa today. So, for UMA, Uniform Memory Access, this bit definition is more than enough to know about Numa. So NUMA is non-uniform memory access, which is also known as distributed shared memory. It is typically interconnection as grid or hypercube. The access to some parts of memory is faster, while the some processor than other of the memory. So unlike NUMA, unlike UMA, UMA it is equally distributed, but in NUMA some memory you can reach faster comparing it to other memories. Numa is harder to program since it is complex. In upcoming video in figure you will see that this is harder to program since it's complex structure, but the scales, it can scale to more and more processors than Numa, right? So what is non-uniform memory access architecture looks like? So to improve the scalability and performance, there are three critical changes which are made to the shared memory multiprocessor architecture. There are non-uniform memory access organization. First, we have to organize as NUMA. Then there is point-to-point interconnect topology, which will be told to you further. Then the other one is scalable cache coherence solution, right? Now, so what is NUMA? In it, all memories can be addressed by all processors, but access to a processor's own local memory is faster than access to another processor's remote memory. Now, I will share you this by an example which our tutor have also taught us, Mr. Indrajit sir. So let us have an example that okay, we I and my processor requirement are in one room. We are in local room, okay, and the other process which wants memory uh, is in another room, okay. So one have to, if I want to achieve, let us say my friends who wants that another memory is in another room, while I want the memory is in the same room, so I can achieve my memory faster. Why? Because it is local memory, it is present at the same site. Why? For my friend, it is not the case. He first have to change the room, go to that room, then look for it. For him, it will be much difficult than me. It will be easier for both, but will be faster for me, right? So this is the benefit of Numa. It looks like a distributed machine, but the interconnection network is usually custom designed switches and or buses. So this is interconnection here. Now these are memories, so all the processors can access to the all the local memories processors as we see here. So these are the Numa. So this is the Numa diagram here as we can see. Now moving on to point interconnect. So an American company named as AMD introduced their point-to-point interconnection hypertransport with the AMD Opteron microarchitecture. The Intel moved away from their dual independent bus architecture in 2007 by introducing the quick path architecture in their Nehalem processor family design. So what was the Nehalem processor? The Nehalem architecture was a significant design change within the Intel microarchitecture, and it is considered to be the first true generation of the internal core series. The current Broadwell architecture is fourth generation of Intel Core brand, which is Intel Xeon E5v4. So now, what is Numa Nusa? So why do we say it Numa Nusa? Because non-uniform memory or cache access, we can say it. So the shared memory as local versus remote memory, you can see the latency between memory to the interconnection network is long, whereas to the local memory to the processors it is short. It is much higher latency to remote memory, as I gave you the example. The bandwidth to local memory may be higher. Bandwidth is the speed of data transmission, as we know. So yes, if I'm standing at local memory, as I gave you the example, so if the exchange between the ideas and the data, we can say here, it will be higher. So yes, the bandwidth to local memory may be higher. Now the performance is very sensitive to data placement. Now let us look at what are the differences between UMA and NUMA. So UMA stands here for Uniform Memory Access, NUMA stands for Non-Uniform Memory Access. In Uniform Memory Access, there is single memory controller is used, whereas in NUMA we see that there are different memory controllers which are used, right? Whereas uniform memory access is slower than NUMA. UMA is slower than NUMA. But NUMA is faster. Why NUMA is faster than UMA? As I told that yes, we can reach to some memories faster. Why? Because of the local memory. Now UMA has a limited bandwidth. NUMA has bandwidth which is more than UMA, right? Non-uniform have more memory than uniform memory access, right? So uniform memory access is applicable for all general purpose applications and time sharing applications, whereas non-uniform memory access is applicable for the real time application and time critical applications. In uniform memory access time is balanced or equal. There are three types of non-uniform memory access limited time is not equal. Yes, we can achieve some memory faster and some other we may slow it down, like we may not reach that memory much faster. but in Yuma it is balanced for each and every memory. Like this is the memory and this is memory access for the processors. So yes, the process can access this memory at the same point in time, and the it will take a same and balanced time, and for this also same and balanced time. But in Numa, here the memory is here, and for this the processor is here, let us say, and the local memory is also here. So local memory can be reached faster, whereas non-local memory, remote memory, can take some time, right? So there are three types of bus which are used in uniform memory access. These are single, multiple, and crossbar, whereas in non-uniform there are two, tree and hierarchical. So the examples of Yuma architecture are Sun Starfire servers, Compact Alpha servers, HP5 series, whereas Numa it comes as Cray TC2000 BPN and others. So these are the diagram representations of Yuma, SMP and Numa. So here we can see that in Yuma the CPU, let me take out my pen from there. So in CPUs we are accessing here the north bridge is connected from by the help of internal bus here, and there is a chipset. This one is known as chipset, right? This whole square thing which is given. This is a for input output controller. South bridge is for input output controller, whereas north bridge is for graphics and memory controller hub. Now these are the PCIs. Here is the memory. Now here Yuma seems a pretty simple diagram, but when we come to Numa, right? When we come to Numa, so this input output is also given to this CPU, to this CPU, and this CPU is also connected to this one. Then this one like this, sorry, this one like this, and from this here it is connected. Like all the CPUs are interconnected. Their memory is local memory. Here what I told about local memory, this is the PCIs, this is input output. So it is more complex. From here you can see and tell, like it is it is more complex, as we can see in this diagram that this will be hard to code, right? That's why we say that Numa is hard for programming, and this is the reason that Numa is actually, we can access more processors by this, but it is actually hard for programming, right? So what are the common differences between Numa and others? By others here I mean SMP. And what is SMP now? SMP is system symmetric multiprocessing, and Numa and CC Numa. CC Numa is cache coherent Numa. So now let us have a look at that. The Numa architecture was designed to surpass the scalability limits of the SMP architecture. With the SMP, all memory access are posted to the same shared memory bus. Now, SMP here stands for symmetric multiprocessing. It works fine for a relatively small number of CPUs, but it will be having problem when we give large number of CPUs. Let's say we have given it a dozen or hundreds or thousand number of CPUs. So this will be these CPUs competing for the access to the shared memory bus. This will be a little harder for SP, right? So this works fine for a small number of CPU. We can conclude by this. Now Numa elevates these bottlenecks by limiting the number of CPUs on one memory bus. In one memory bus, we limit the number of CPUs so that we don't have a havoc created for the competition of access to the shared memory bus. Now the connecting the in Numa, we connect the various nodes by the means of high-speed interconnect. Now, what is the difference between Numa and CC Numa? On the big scale, this is not distinguishable. Now, let us have a look at that. What this tells. The difference is almost non-existent. As I told you, CC Numa stands for this. Yes, Numa and CC Numa have really come to be synonymous. Yes, since they have no difference, so we can call them synonyms. The applications for non-cache coherent NUMA machines are almost non-existent, and they are a real pain to program. Yes, as I told you, NUMA is only real pain, but non-cache coherent is also the real pain for program. So unless specifically stated otherwise, Numa actually means CC Numa. If they have stated, okay, this CC Numa is different, then that is another thing. But in basic level, these both are actually same or synonyms, right? What is Numa node architecture? Numa architecture is common in multiprocessing systems. These systems include multiple hardware resources, including memory, input-output devices, chipsets, networking devices. As I showed you in that image, or you can say that diagram, each collection of resources is a node. Multiple nodes are linked by a high-speed interconnection or bus. Every Numa system contains a coherent global memory and input output address space that can be accessed by all the processors in system. The other components can vary, although at least one node must have memory, yes, and one must have input output resource, and the one must have processors. In this type of memory architecture, a processor is assigned a specific local memory for its own use, and this memory is placed close to the processor. The signal paths are shorter, which is why these processors can access local memory faster than non-local memory. Also, since there is no sharing of non-local memory, there's an appreciable drop of delays, latency when multiple across access requests come for the same memory allocation, right? So what are the advantages and disadvantages of Numa? So one of the biggest advantage of Numa, as I told you, is the fast movement of data, the bandwidth, and the lower latency in the multiprocessing system. Additionally, Numa reduces data replication and it simplifies programming. By data replication, it simplifies programming, and the parallel computers in a Numa architecture are highly scalable and responsive to data allocation in local memories. What is the disadvantage or biggest pain for Numa? Numa can be expensive, and the lack of programming standard for larger configurations can make implementation challenging. As I showed you in the diagram, so from diagram you can conclude this point, right? Now, what is the example of Numa CM5? So this here is the example of Numa CM5. Here you can see that these are processing nodes, right? This is hippie and this is a LAN. Here we have RISC microprocessor. So here we have fetch the instructions by program control. This bus is 64-bit bus, right? You can show that, okay, this one here, why don't you ask that this one should be Yuma? But no, this is not a Yuma. Why? Because there are the memory is accessible from all the processors, and it has a local memory. So floating point vector processors are there, and vector units are accessible to the memory even, and for the same for both of them. And these are the two data network and control network things, right? Each processing node of the current implementation of this CM5 consists of a RISC microprocessor, 32 MB of memory, and an interface to the control and data interconnection network. The processors also include 4 independent vector units, each with a direct 64-bit path to 8 MB bank of memory. Double This gives a processing node with a double precision floating point, which is a rate of 128 MFLOPS, and a memory bandwidth of 512 MB per second, right? So these are the references I refer to for all my Numa preparation for this video, and I would like to give the credits even to these websites, and some of them are research papers as well. And so I would like to rest my words here, and thank you so much guys for watching.